Alright, so on Friday we had a look at the first derivative and not just how to find it. We obviously found the first derivative last term, but the fact that the first derivative tells us about the gradient of a tangent to a curve and whether it's increasing or decreasing for certain values. Well, if the first derivative tells us about the gradient, the second derivative tells us about the concavity. So very simply put, just as a little side point, to find the second derivative, you just take the derivative of the first derivative. So we've done a little bit of that today in class, and what we're looking at here is that if we have a first derivative, so if I've got some function y equals fx, well, what it means is that if I find the first derivative and then the second derivative, if I've got f double dash x and that is positive, it means that I've got a section of that curve, or for those values, the curve is concave up. If the second derivative is less than 0, if it's negative, it just means our curve is concave down for that set of values. And then if our second derivative is 0, if our second derivative is equal to 0, it means what we've got is called a point of inflection. Now, basically what that means is we've got a change in concavity, typically. So it's, again, much like those turning points that I talked about on Friday, where they're normally a stationary point, where the first derivative is 0 is normally a turning point, but not always. There's some examples. It's the same here, where if our second derivative is 0, that's normally a point of inflection. It normally means we have a change in concavity. It's almost like where a concave up part of the curve connects to the concave down section, but that's not always the case. So it's typically is, but not always. Second derivative also tells us the rate of change of the first derivative. So again, if our curve were concave up and our first derivative were positive, that means that the gradient there is going to become steeper. And there's a whole bunch more scenarios here that we'll look at, but I think it's easier if we do this visually. Alright, so here I've got a cubic function, and we can see a few things about this. We can see where it has x-intercepts or roots, we can see where it has a y-intercept, but the main thing I want to look at here is concavity. So if I start all the way down here, and I'm going to move to the right, if I start moving along this section of the graph, and I'm just going to start drawing some tangents here, you'll see that what I've got, and that's not an exceptionally drawn tangent, but you can see that has a really steep positive gradient. So over in this section over here, I think we could pretty comfortably say that the first derivative is positive. And what's going to happen as we get towards this turning point is that our tangents become flatter and flatter, and eventually, at that point there, it's horizontal. So we can break our graph up and say, all right, over here, our first derivative, let's just call it y dash, is positive. We know that our first derivative is greater than 0. And the same can be said over here. We kind of talked about this idea on Friday, that over here to the right, again, I'm going to have very positive gradients and getting more positive as well. It's obviously steeper up here than it is just down here. So over here as well, y dash is also positive. Now in between here, in between those two turns, we've got really negative gradients. And what you'll find is that it's sort of, let me just rub some of this out so you can see it a bit clearer. I think if we were to draw a tangent there, that's steeper than horizontal, obviously. But if we were to draw a tangent down here, what you find is that it's really steep. And the same deal, what you'll find is that if we were to draw a tangent down here, well, again, that's becoming pretty flat as well, and we know it's going to become horizontal at that point again. So what's happening in this section is that our first derivative is negative in the middle there, so y dash is less than 0, but something is making that gradient change, because obviously if we trace along this curve, I'm steep negative, steep negative, steep negative, and then somewhere in there it goes flatter, 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 negative, and then it stops again. Now what's actually causing that change there, and the change in these gradients over in this section as well, is the fact that we have a second derivative that changes as well. So what we're saying is where the curve is concave down, now the curve is concave down if we have a look at it. I hope you can see that all along this section it's concave down, still down, still down, still down. And then over here it's all up, 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 up. And somewhere in there we have a change in concavity. We have our change in concavity in the middle. Well, what we call that is a point of inflection. Okay, it just means that our curve in this case changes from concave down over here to up over here. And where that occurs is called the point of inflection. So over here what we could say is everywhere to the left of this point is y double dash is less than 0, and everything to the right of this point y double dash is greater than 0. And by looking at the second derivative we can actually work out what's going on with our curve in terms of its concavity. So there's some graphs in the theory notes for you to have a look at. The combined looking at for small sections of the graph of a certain graph, looking at the first and the second derivative and seeing what it looks like where the first is positive and the second is positive and the first is positive and the second is negative and so on. There's 4 of them. Have a look at those. But I'm going to do the example just below that. And what we're asked to look at is this curve y equals 3x squared minus 2x cubed. And where is it concave up? Now we know that's a cubic. It's going to have a couple of turning points, and then it's also going to have a point of inflection. So part of the curve is going to be concave down, part of the curve is going to be concave up. Because this is negative, well, it means that the right-hand part of my curve will be concave down and the left-hand will be concave up. But that's just me knowing kind of what it's going to look like. What we need to use is the first and the second derivative. So we go find our first derivative. Our first derivative is 6x minus 6x squared. Now if I were to look at this first derivative, I could go find out about the gradients. Okay, I could go work out where it is increasing and where it's decreasing, but that's not what we're asked to do here. So I'm going to go find the second derivative, which is just 6 minus 12x, again, just the derivative of the first derivative, using our standard, most basic method of differentiation. And now I've got some function that represents the concavity here. Well, if it's concave up, I know that I'm going to have y double dash being positive. So all I'm going to go and say is, therefore, 6 minus 12x is greater than 0. Okay, well, we need to go solve this. There's a couple of ways we could do it. My inclination of what I've written in your notes there is to factorize it. I'm going to here solve it by treating it like a linear inequation and manipulating it that way. So I'm going to have minus 12x is greater than minus 6, and x is less than a half, simply by dividing by negative 12 there. Means I have to change that sign, flip it in the other direction. And that makes sense as well. Because if I made x really big here, let's just test it. If I picked a value like x equals 5, clearly 6 minus 60 is going to be negative, which means it's going to be concave down. But if I pick any value where x is less than a half, so let's say 0, well, that would be 6 minus 0. The second derivative is positive, and it means it's concave up. So any value of x less than 1/2 will give me a section of the curve that is concave up. And then any value greater than a half will give me concave down. At a half, at x equals a half, we have a point of inflection. So the curve, very rough sketch, looks something like this. This is our value for a half there. What it means is we're concave up, and then there we flip to down. Now it's got those turns. I have no idea what those 2 turns are. I'm not particularly interested in what the intercepts are. That intercept should actually be through the origin. I'm just talking about the concavity. It goes from up to down. At that point there, x equals a half. Excellent. And the second example here, we're asked to sketch the curve y equals fx given f of 2 equals 3, f of 5 equals 7, the first derivative is positive and the second derivative is negative. Okay, for a domain of x between 2 and 5. Okay, what does all that mean? It seems quite confusing to start with. Well, f of 2 equals 3, all that means is when x is 2, y is 3, so it passes through the point 2, 3. That means for that domain, we're going to have some sort of sketch where I've got a start point and an end point. It's only a very small section of this curve. It means we've got a start point of 2, 3, and similarly, if when x is 5, y is 7. So that first piece of information, their first two pieces, f of 2 equals 3 and f of 5 equals 7, that's all that means. Now, f dash x is greater than 0. Well, what does that mean? If my first derivative is positive, well, that means I'm increasing. Okay? It means I've got positive gradients. So we know that. We know that if I'm going to draw gradients along this curve, sorry, tangents on this curve, their gradients will be positive. And similarly, if I look at f double dash x being less than 0, well, that means I'm concave down. Okay, what it means is those positive gradients are going to become less positive. The gradients are going to become flatter. So let's start by labeling our 2 points approximately. I'm going to say that's 2, 3, and that's 5, 7. That's just some estimate there. And then 5, 7. Now you'll notice I've labelled them with solid dots. The reason I do that is actually it's better to label it with an X, but here because it's a fixed domain, we're not going to have end arrows on that, we're not going to continue it infinitely, it's just for this very fixed section of this curve. We don't know what's going on with the first and second derivatives for other parts of the graph. Once I sketch it, you'll see it looks like it might have a turning point somewhere, and we don't know about that. We just know for this little section here. So actually, rather than marking it with X's on the end like that, I actually have to mark it with solid dots at the end to show that we are very fixed between those two values of x equals 2 and x equals 5. And what you'll see is, well, we end up looking something like this. Okay, now if I was to draw, well, clearly it's concave down. And if I was to draw a tangent there, it's positive. But as I move further to the right, it's becoming less positive. Okay, now that just simply means that our first derivative, I'm just going to get rid of those to make it a bit neater for you. Our first derivative is positive, but our second derivative is negative. It's increasing, but at a decreasing rate because the second derivative is negative.